Okay, welcome. Okay, so it's this emotion says. Okay, we can start. So today we're fortunate to have Dr. Harmon to give a colloquium. Okay, he got his PhD 2010 from Ohio State University. Afterwards, then he worked at the University of Iowa from 2011 till now. And so today he was going to talk about spin-related problems. And he was expert on spins. Then the floor is yours. Before that, and thank you for a distinguished speaker from the department. A small token.
Thank you very much. Appreciate that.
And the floor is yours.
Okay. Well, thanks for the introduction. Thanks for inviting me here to talk today about, I think, what are some new areas in physics that are very interesting and I think could have impact on the world in the coming decades. And they're related to spin and mainly coherence and also the relation between different spins. And what's important is that this is happening at room temperature, which is, of course, where we want things to happen if we want to use them for real life. I'm going to motivate the talk by this static-looking picture here, which is actually a concrete brick. And my question is, can a fly, okay, there should be a little fly, oh, maybe that's a little fly. Can the fly push over the brick? That's sort of a rhetorical question. Well, maybe if it's a really big fly, but that's cheating, so we're talking about a real size fly. Can it push over this brick? And there's analogy, of course, I'm not just spouting out nonsense here, there's analogy in physics where we can add a very little bit of energy into a system and see very large effects come out. So, as Gia mentioned, I am coming here from the University of Iowa. I worked with Michael Flatte, who is a professor there. This is our building here, which is shown here, that houses this Optical Science Technology Center. It's not actually a physics building. And then here's the Iowa River that flows beside it. And you might say, oh, this is a really nice location for a building. And it is about 75% of the time when you're not having to evacuate for floods. It's still not too bad. So here's an outline. I'm going to start really basic and talk about why we care about studying spin. I'll give a brief history of spintronics, which is sort of the merging of spin with electronics. I'll talk about the emerging field of quantum spintronics. And I'll talk about a couple of my projects, namely this magneto-electroluminescence in certain types of OLEDs. And this will be the last topic, which might run into the end of the time here, but it's dealing with defect-mediated transport at interfaces between magnets and metals or semiconductors. So why do we care about spin? I think as physicists we're naturally curious, and for so long spin has been getting a free pass, a free ride in our technology. And I think it's somewhat unacceptable. We would like to use it, try to harness it, and use it to our benefit. But of course there's practical reasons, is that over the last decades we've been pushing conventional electronics to their limits. And some people supposedly can cook their eggs on their laptops. I haven't seen it done. But and the basic idea is that pushing charge creates heat, and changing spin is a much smaller energy change than moving charge. So there might be some benefits to using spin. This is a little bit maybe naive of a thought, and I'll talk about that shortly. And then I think the most interesting part, though, is adding magnetic functionality to these electronic systems. That you're merging electronics and magnetism through the spin. So we're already using spintronics, really, and we're using the first generation of spintronics, which was metallic spintronics, discovered in the 80s by Ferrer and Grunberg, who were awarded the 2007 Nobel Prize. And the phenomenon they discovered was called giant magneto-resistance, and it's best explained in this simple little diagram here, where you have a ferromagnet sandwiching a non-magnetic metal, and then another ferromagnet. And when the two magnetizations are parallel, you can think about sort of, you have this good band matching between the up bands and the down bands. And this allows for a lot of current to flow in a low resistance state. Whereas if you have them anti-parallel, your bands are poorly matched and you have a high resistance state. So you can basically think about these as different spins have different resistances when they travel through this type of device. And of course, the way you change these orientations of the ferromagnet is through magnetic fields. So that's why it's a magneto-resistance effect. Now, the GMR actually probably isn't really used in much of the modern electronics. It's been developed much further, namely in TMR, tunneling magnetoresistance, which replaces the metallic interface with an insulator. So you're now relying on tunneling between the two ferromagnets. And this can create actually much larger magnetoresistances. And these are used in this emerging technology, which may have been emerging for about 10 years or so now, but some people are still hot on it, MRAM. And you're using currents, like these bars here I think are currents, and they can manipulate the magnetic tunnel junction through their Oersted fields. Another way that's more recent to control magnetic bits is through spin-torque transfer MRAM. And this is applying a spin current between the two ferromagnets. And when you have a spin current going through a ferromagnet, that spin current affects a torque on the ferromagnet. You can rotate that ferromagnet or change its orientation. So metals are good and all, but we know that semiconductors are even more important for our current transistor-based technologies. And if we could open up the playbook for spintronics and semiconductors, we might get even more usage out of these systems. And it was really started in about 1990 with this paper by Da and Das from Purdue, where they proposed a spin field effect transistor. And it's quite simple to understand. We again have a ferromagnet source and drain, and we have this gate here. And when the gate is turned off, there's no voltage. You have spins transporting from one side to the other. This would be a low resistance state. Now, if we turn on the gate voltage, instead of moving charge onto the gate, the way that we're going to affect the current through the channel is through a magnetic field. When you turn on the gate, you create an electric field, which can create an effective magnetic field through the Rashba effect. It's not that important, but it's creating some magnetic field that rotates the spin to an anti-parallel alignment, which then is a very high resistance state. This resulted in a flurry of research on different types of devices similar to this. A lot of research into the fundamental physics of spins in semiconductors, but actually creating this device is, I don't think, yet been achieved. There's some there's some pretty big problems though with this type of device, in that to actually be commercially relevant, to have commercially relevant on-off ratios, which tells you that basically the amount of current from the gate on and gate off, you would need to have very pure spin detection and injection efficiencies, 99.9995%, whereas only 70% are realistic right now. And additionally, the electric fields to rotate the spin would have to be very large, or you'd have to have very long channel lengths to affect that type of rotation. And that sort of defeats the purpose of having these large transistors. So this doesn't seem to be the best way going forward, but semiconductor spintronics has still been a very flourishing field along many different avenues. The spin Hall effect is one major component in the field where a charge current induces a transverse spin current due to the spin orbit effect. And also spin pumping is very popular, where AC magnetization in a ferromagnet can induce a spin current in a metal or semiconductor. So I'm not going to talk about these areas. Instead, I'm going to talk about what's been coined as quantum spintronics. And these are effects that rely on spin coherence and spin correlations near room temperature. And it's primarily concerned with how these coherences and correlations can affect very large changes in the properties, like light emission and charge transport. So here's my little spintronics family diagram. We have metals here. We have semiconductors. That's seen the bulk of the research in the past several decades. Then in the middle, we have hybrid systems that use both. And then now we have quantum spintronics, which is going to rely on more disordered materials with localized states, such as using defects and NV centers in diamond or silicon carbide. And then, of course, we'll have some overlap with these other systems, which I think is still unknown where that will go. And then I think neat about the quantum spintronics is that it's able to maybe bring in new fields into the physics community or the spintronics community. One would be medicine, which I will give one little example, and biology. And mostly I'm going to talk, though, about the relevance in energy, namely trying to improve efficiency of OLEDs. And my last topic will be on maybe something in this area. Okay, so back to the brick and the fly problem. And when I got into this field, I read this quote here that the study of magnetic field effects on chemical reactions has long been a romping ground for charlatans by a physical chemist at Oxford in 1975. Not exactly a glowing endorsement of the field, but at the time, some of the physics theory was quite controversial, and it's indeed related to this brick and the fly experiment. And it's because people were finding that magnetic fields could have effects on chemical reactions. And this is somewhat surprising, because chemical reactions depend on bonds, and bonds have very strong, very large energies on the order of electron volts, which are much larger than room temperature for one, and which is much larger than the energy in a magnetic field. So the magnetic field we're going to be talking about are much less than a Tesla, maybe 100 millitesla or even less. So those energies are only micro electron volts, whereas KT is 25 millielectron volts. So very different energy scales here. So it is surprising that a magnetic field could affect very large changes in materials. So the trick to the fly on the brick is that we cheat. And instead of having the brick like that, we're going to lie it on its edge. And essentially, we're creating a non-equilibrium state. And once it's precariously balancing on the edge, the fly can land on it with just enough force to push it over. Okay, so now I'm going to try to show you how this works in a in a device, and this is going to be an ugly slide. I hope you can bear with me. It's not as bad as it looks. I'm going to step you through it. Just to remind you, when you have two spins, they form either singlet states or triplet states. And the triplets are symmetric, the singlets are anti-symmetric. And how they form with the orbital wave functions, how the total wave function is formed depends on the symmetry of the orbital wave function and the spin wave function. They need to be anti-symmetric for fermions. So here's the example now I'm going to show you. I'm going to look at a molecule with a HOMO level and a LUMO level. And this is the highest occupied molecular orbital. This means lowest unoccupied molecular orbital. And you can think about it as a valence level if you want. And if light is incident on the molecule, it can excite it. So, and just to be clear here, in the ground state, the HOMO level is filled, and it needs to be in a singlet state. And this is dictated by the Pauli-Exclusion principle. You need to have opposite spins in the same orbital state. So light comes in, excites one of the electrons to this higher level. Okay? And I'm going to map down here the energy here. So here's the energy of the ground state. Now here's the excited state, which is an exciton. It's an electron hole. We can think about this as being the absence of an electron also, so it has a positive charge. So this is an electron hole pair, and they're formed in the singlet state, and it's excited, so it is a higher energy. Now, dissociation can occur where this electron here hops to some other molecule in the system. So now it's not on the same molecule. This is empty. This is a different molecule. And we're going to call this a polaron pair. So while they're not on the same molecule, they're still coulombically bound, but they're on separate molecules. They could be several molecules away from each other, but they're still feeling that Coulomb attraction. And they're still in the singlet state. Now, this is a less bound state, even more, so it has a different energy. We're going to call that the singlet again up here. Okay, so this is where it gets interesting. Now, we can have two different processes. We can have, okay, so now, since these are not so close together, we can have what I'm going to call spin mixing. Okay, so here is the Louisville equation. Rho is the density matrix, which is essentially just putting all the information about the spins into a 2x2 or 4x4 matrix in this case, because we have two spins. And then it evolves. This tells you the evolution. This is the Hamiltonian, which could be some different magnetic fields and whatnot. And essentially, in some sense, you can think about this as the Schrodinger equation for the spin. So this now we have these different interactions in the Hamiltonian acting on the polaron pair. Now, they can act on the polaron pair because the singlet and triplet levels of the polaron pair are nearly degenerate because the two polarons are separated. So the exchange energy is much smaller. And this essentially is now the fly in the ointment. Okay, we've got this non-equilibrium state as a singlet, and now we can easily change it into a triplet with a magnetic field, a small magnetic field, because there's no energy difference. So you can have these polaron pairs be triplets, or you can have these polaron pairs be singlets now, under this influence of the Hamiltonian. And further on, you can recombine. So now this electron can come back to the original molecule and form either a triplet exciton or a singlet exciton. And the triplet exciton will be at a different energy than the singlet. This is due to the exchange energy. Okay, so hopefully that wasn't too awful, but I'm going to now combine all these energies into a Jablonski diagram, which tells you, this is the most important thing now to think about in these excitonic systems, is we have energies for the singlets and triplets, polar ion pairs, and those, remember, far apart, and they're about to degenerate, and you can have spin mixing between them. That's evolution of the spins in the magnetic fields. That means you can change from singlets to triplets and vice versa. Then you have some rates for the singlets and triplets to recombine into singlet and triplet excitons. This is coming back now, back onto the original site. And these rates can be different, mainly due probably to the different orbital wave functions on these different sites. But we wouldn't necessarily expect Ks to be that much different than Kt. And if we think about the triplets here, the excitons that form, they're stuck. Because only singlets can recombine radiatively and give off light due to the spin selection. So it turns out that you can have some luminescence from triplets through phosphorescence, but it's very weak, and I'm going to ignore it for the purposes today. So most of your luminescence is going to come out of these singlet excitons, okay, as they decay back to the ground state. Okay, so this is believed to be occurring in birds in how they navigate in the Earth's magnetic field. Light excites these molecules, which create singlets, and they can pick up triplet character in the Earth's magnetic field, which must have some directional dependence, and they evolve, and this can change the way they recombine in the molecule. And this has been researched a lot over the last few decades, mostly in the last 5 years, and it's believed this particular molecule here, called a cryptochrome photoreceptor, is responsible. There's also evidence that this can inhibit tumor growth by the fact that you're creating these free electrons, basically not free, but these more delocalized electrons than they were before, which we call free radicals a lot in the field of chemistry, not so much in physics. And free radicals are well known to be harmful to cells. So it's possible that these magnetic field effects in a tumor cell could be inducing harmful effects to those tumors through the free radicals. Okay, so now I'm going to get into the real meat of the talk and talk about immense field effects in OLEDs. This work was done in collaboration with experimentalists at Iowa, Professor Marcus Woganot and two of his grad students. So here's a little intro to the OLEDs. Essentially electrons and holes. Here's your anode and your cathode. In the middle here, you have an organic semiconductor. And you inject electrons on one side, holes on the other side. And there's an electric field, so they tend to flow to the other side. They meet up in the semiconductor, forming triplet excitons or singlet excitons. And as I said before, the triplet excitons are relatively inert, and singlet excitons are what gives us our light. Now, due to the spin statistics, you can see that you only have 25% of these pairs being emissive. You're wasting a lot of what's going on here. So we'd like to get around that. And one way you do that is through this phosphorescence by putting in very large metals that have strong spin-orbital interactions. I won't talk about that. So in these excitonic systems, we can apply, in these OLEDs, you can apply a magnetic field. And that's what we're showing here. This is the magneto-electroluminescence, or MEL, versus magnetic field. And we can see percentage changes of about 15% or so. That's about the largest we've seen in what I'm going to call excitonic materials, where we're forming excitons in the organic semiconductor. And the reason, well, just to reiterate, is that the spin mixing is happening at this stage of the polar ion pairs. Okay, and that's going to be important. And I should now probably tell you what exactly is the spin mixing, what's causing it. And in this system, it's believed to be due to the hyperfine interaction. Just to rehash what that is, in organic molecules, you have a lot of hydrogens, you have a lot of carbons. Carbons have very few magnetic nuclei. So they're not really going to contribute much, but hydrogens have a lot of spin 1/2. So here's just an example of penacene. And all these little arrows going around signify the random hyperfine fields from the nuclei, from the hydrogen nuclei. And we're at high temperatures, so of course these are random. We have a lot of them, so we can add them up. You get some semi-classical vector out, VHF. And if we're at 2 sites, okay, these 2 shades are maybe 2 different sites, 2 different molecules, we have 2 terms in our hyperfine Hamiltonian. And how the spin mixing will occur now is that if we start out maybe in the T0 triplet state, over time, under the influence of the hyperfine Hamiltonian, we're going to induce the other 3 spin states, singlet and other triplets as well. And here's sort of a very classical look at it with the electron spins processing around these fields. Now, when we crank up the magnetic field, the external magnetic field, we're going to change the energy splitting here. So in 0 field, we have mixing between all 4. In a large field, we only have mixing between the T0 and singlet spin states that are responding to the Zeeman effect. So the T plus and T minus states are splitting off and kind of getting out of the picture here. So the external magnetic field then is essentially reducing the amount of spin mixing by getting rid of these states. So, excuse me. Now I'm going to talk about the thermally activated delayed fluorescence. And this is a new phenomenon discovered a few years ago by some groups in Japan in OLEDs to maximize the internal efficiency. And imagine, so here's our basic picture of excitons. Okay, spin mixing is occurring up here. And we have this large exchange splitting here, which is on the order of electron volts. Now, if we could reduce the exchange splitting of the exciton maybe to something like this, we could have these excitonic levels, the single and triple excitonic levels, much closer together. And so close together, maybe we can get spin mixing between them. Okay? And here you can tell now that the spin mixing happens here, where you have a very strong recombination right here and essentially 0 here. So the spin mixing is happening between 2 very different states in terms of how they're getting back to the ground state. Whereas here the spin mixing occurred between Ks and Kt, and these rates were very similar to one another. And this has large effects on the total magnetic field effect. So another thing is, since you might not be able to get these to be as degenerate as you want, well, you can get them close enough where you can see activated behavior. So you might expect to see larger or more fluorescence with increase in temperature. And that's what's shown here. The red, or the short time, is going to be the fluorescence of these singlet pairs. And then the phosphorescence is this longer time scale. You can kind of see it takes a while to decay. Now, and the black is at 300 Kelvin. And now we see the short time scale again, but then we have this longer but not really long time scale. And that's believed to be this upconverting of the triplets to singlets. And this is allowing you to convert those wasted triplets, they were wasted before, sitting there. Now you can convert those back to singlets. So before we had quantum efficiencies of 25%, and through this mechanism, you can increase it to over 90%. So what does this now isn't excitons. It's something called exaplexes. So here's the exciton. Here's the positive and negative charge on the one molecule. Exaplexes are positive and negative charge on 2 adjacent molecules. And you can see why this would change this diagram now. Well, you have much less spatial overlap of your wave functions, so you have a much smaller exchange energy. So your singlet and triplet levels are getting brought together and allowing for this upconversion to occur. So at this point, okay, so here's really now what we've been doing in Iowa and in the experimental side, is that we've looked at one of these TADF, this thermally activated delay fluorescence system. This is one that's used popularly, MT data and 3TBYMB. And these are co-evaporated blends, so essentially putting the molecules together, trying to maximize the adjacency of them. Okay, so you want these to be next to each other. And we're running, of course, a current through them. And then we measure the change in electroluminescence with magnetic field. And in our pristine device, which I'll define later, this change is up to 60%. So recall that before, when we were dealing with the excitonic system, it was only 15%. So 60% is quite a large increase, the highest seen so far. Now, before I was saying, was the hyperfine interaction relevant for the excitonic system? However, everything about this is screaming that it's not the hyperfine interaction. And the reason why is that in high fields, the hyperfine interaction is suppressed. So you would reduce your amount of spin mixing, which would reduce your amount of triplets going into singlets. So you actually would expect a negative magneto-electroluminescence. So this is a question we asked, why is it a large effect? And also, if it's not the hyperfine interaction, what interaction is it? Okay, so at this stage, I came in and looked at this, looked at how to model this system theoretically. And just to review this again, this is the Liouville-von Neumann equation, which describes the coherent evolution of the spin density matrix. So this is describing coherent dynamics, spin precession magnetic fields, spin-spin interactions, and many more, of course. And of course, it's not just limited to spin. Now, we have these stochastic processes occurring, these different recombination rates. So we would like to somehow put that into this sort of Liouville type theory. And the way to do that is through something called the Lindblad equation. So here's our old coherent part. And then we're going to add in this Lindbladian part, which is composed of several different operators. But essentially what it's doing is you're syncing out certain states. This is actually preserving the trace of the density matrix. But you're sort of syncing out states and putting them in different states. You're sort of mixing it up. And you can think about that as sort of decoherence and dissipation. And kind of to put this on some firm footing, you can derive the phenomenological block equations out of this type of model using these Lindblad operators, where the L1 and L2 describe relaxation, that's flipping spins from up to down, and decoherence, where you're dephasing spins. And these are terms used this is used often in NMR, ESR. So how do we apply this in our case? Well, we actually aren't really concerned about preserving the trace, believe it or not, of the density matrix. So we actually kind of simplify the Lindblad equation, and we're only going to look at these anti-commutator terms, which are going to remove certain states out of the density matrix. So the PS and the PT, those are projection operators, and then these terms are going to remove singlet and triplet states accordingly at rates Ks and KT. Now, so as I said before, if we want to rewrite these Jablonski diagrams, in the excitons we have Ks approximately equal to KT, and in the exaplex energy diagram we have Ks much greater than KT. So these are very different realms of these recombination processes. So I've calculated the MEL for hyperfine. So here's the MEL, magneto-electroluminescence, and here is KT over KS. And since we're in the exaplex system, we know KT is about 0. So 0 is down here, predicts the negative magneto-electroluminescence, like I said, we would expect, just kind of qualitatively. Now in the excitonic system, which is on this realm, when KT is approximately 1, or maybe a little bit greater, you see the positive, so 50% or so is around here. So makes sense with our expectations. So however, this is completely inconsistent with these exaplex systems, or with our observations, which we're measuring 60%, not negative 40. So what is the mechanism that is doing this mixing? Well, we believe it is the delta G mechanism. So the G factor gives the proportionality between a magnetic field and its precession frequency. And while it's approximately 2, in real systems, there are variations between different molecules, and there's anisotropy also in the G factor. So, and despite, the percent changes are very small, of course, 2.01, 2.011, but these are well studied in organic radicals, so it's not out of the realm of possibility. Also, our electrons and holes are in different type of molecules, so you might expect more drastically different environments, so you might have a larger delta G. Also, exaplexes are more delocalized than excitons. So they're going to be spread out over more nuclei, and as you spread out over more nuclei, they're going to tend to average out, sort of as a 1 over square root of n. So since they're spread out over more nuclei, you expect smaller hyperfine coupling. And just the little cartoon picture here, we have some applied field, we have some spin starting out at T0 here in the triplet state. And if you have no delta G, they're going to precess around the magnetic field, and at some later time, they're still going to be in that same state. They haven't changed their relative orientation. Delta G not equal to 0, they're going to precess now at different rates, so you have some change in orientation at a later time. It picks up some singular part. So now we've run the calculation with the delta G mechanism. So essentially, you can get rid of the hyperfines out of the Hamiltonian. And we've also had to put in dissociation of these exaplexes, which you might expect to be a larger effect in hexaplexes than excitons, since they're, again, more widely spaced. And here is the calculation. So again, this is versus KT over KS. Okay, and then again, on the left then would be the exaplex where KT equals 0, and on the right would be excitons. And we see that we can get a maximum of 100% when, and GT over GS is essentially saying how degenerate are your singlet and triplet levels. And if GT over GS is 1, that means they're exactly degenerate, which we know is the case. But theoretically, we can get a maximum of 100%, but maybe more realistic values around the 40 or 50% that we observe. So why 100%? Well, what's happened is that we've changed all of the T0 triplets into singlets. So we've doubled our luminescence. However, the other two type of triplets that aren't mixed with the delta G mechanism are still there. So there might be other ways to get around those and get those two to be converted. And this is just comparison to hyperfine mechanism. So you can see the very drastic different behaviors. So that is why we think it's the delta G. Now, this is where things got interesting, is that when we ran current through these devices for long periods of time. How am I doing on time? Oh, sorry. Okay. 10 minutes. Okay, when we ran current through these devices for extended periods of time in large currents, these tend to induce traps in organic semiconductors. And it produces highly nonlinear IV and EL versus V curves. So here's EL versus voltage, and at 0 conditioning, 0 minutes, they're calling it, we have some V to the 6.5, and at this 15 minutes at 0.2 milliamps, we have V to the 29. So a huge increase in this exponent, extremely nonlinear. So here's the pristine device, where we measure the 60%. Now in this highly conditioned device, we measure 4,000%, which is just extremely large. It's maybe among the largest magneto-resistances ever measured, compared to like much larger than I think TMR. So I think some systems you might get like 6,000. But it's extremely large. And so yeah, this is, so here's a picture. Yeah, here's a magnetic field turning on and off, and it's very obvious the large changes in luminescence. So it's kind of neat. Okay, so so the large effect is partially coming from this strong nonlinearity in the IV relationship, but it's also coming from some other changes as well. And I've done the fitting basically the theory to the data, and we can extract certain parameters such as this exchange splitting between the singlet and triplet exit plexus. And we find that by increasing the conditioning, we're decreasing this exchange splitting. And of course, this is consistent with an increase in the magneto-electroluminescence. So we don't really have a good picture of what the conditioning is doing. However, we believe it's some morphological change, possibly that are trying to separate exit plexus further apart, since we have a smaller exchange energy that's consistent with our exit plexus being further apart. So of course, these very large magnetic field effects might have some use in magnetosensor applications, but another important result is that the electroluminescent power efficiency increased by 30% in these magnetic fields. So this does indeed increase the efficiency of an OLED device. I should state that these OLED devices we used weren't, top-of-the-line OLED devices. They're more, single layer, I think they call them. So there's, of course, a lot of work to be done on more relevant devices that are used in technology already. So there is a large resistance in these devices, which of course is undesirable. We need to find out what exactly this mechanism is and possibly search for material combinations that have higher conductivity and but maybe smaller delta ST. So our delta ST we get out of here is 22 MeV. So there's a lot more room to decrease that further, which would further increase the magneto-electroluminescence. Okay, so I'm going to talk a little bit about this, what looks like to be a very different project, and it is in a way, but it has some similarities with what I just talked about. And it's these interfaces, defects at interfaces of semiconductors and magnets. And this was done on the experimental side at Stanford with Professor Huang and Adrian and Hisashi. So this is sort of going back to the semiconductor spintronics area now. An important aspect of that work is spin injection, injecting spins from ferromagnets into semiconductors. And how do you know if you've actually done that? Well, the prototypical way to figure that out is by applying a transverse magnetic field to your ferromagnet. Okay, so when you put spins into the semiconductor, they'll process around that transverse magnetic field. And this is called the Hanley effect, and it's very simple to calculate how that works. You have dsdt, where s is your spin. you have the magnetic precession, and then you have spin relaxation. Spin relaxations occurs whenever you have some non-equilibrium spin, which is the case as if you injected it. So you solve this equation very simply, and you get some Lorentzian line shape. So then in the lab, you change your magnetic field, and you measure an appropriate voltage, and you can measure these different line shapes. And this tells you that you do indeed have spin in your semiconductor. Now, I won't get into all the history of this, because it's quite long, but recently there's been reports of spin injection that show Hanley effects, but they also show some other features that make people really scrutinize whether it's occurring or not. And that's they show an inverted Hanley effect, which you do not expect. If you apply a magnetic field parallel to the spin, you don't expect to see any spin precession. You shouldn't really see any effect. But they do see this inverted effect as well as the normal effect. So we see both. Additionally, these widths, they correspond to spin lifetimes, spin relaxation times. And the values you get out of these fits here are completely at odds with much of the theory and also much of other experimental methods. So for instance, in gold, this is permalloy, you have a tunneling barrier in gold, they measure 150 picoseconds for your spin lifetime, where it's known to be only 1 picosecond. So this is led people to ask, what actually are you measuring? Because it might not really be spin injection in the semiconductor. And an obvious candidate might be that you're seeing something in the defects that are in the insulating barrier. And the group at Stanford performed experiments on strontium titanate with LaO, lanthanum aluminum oxide, tunnel barrier, and cobalt as their ferromagnet. And they measured these Hanley effects, both the inverse and the regular Hanley effect, which are these dash curves. You can ignore these higher field solid curves. These dash curves are the inverse and normal Hanley effect. But they also did inelastic electron tunneling spectroscopy. And essentially what this technique does, it tells you how much current is going through the localized states in the insulator. And they see extremely similar curves as they did just in the normal DC case. So this is strongly, they see the same magnetic field effects essentially. So this is strongly indicative that something is definitely important going on in the localized states. So I've modeled this theoretically now, looking at a defect in this insulating barrier, and we're injecting spin and charge from the left into the defect, which can then hop to the ferromagnet. Now, if the spin is parallel to the magnet, you're okay to go, right? You're a majority spin. 5 minutes? Okay. If you're anti-parallel to the ferromagnet, you're going to be blocked. So this looks very similar to what we saw in the OLEDs when we were blocked from creating these triplet recombinations, but we could create the singlet recombinations. So this is sort of this what I call the spin correlated physics at play here. You need to have a certain orientation of the magnet and the spin to have current go through the system. So then if you have a local field, which could be hyperfine field at this site, it can start changing the relative orientation of the electron spin in relation to the magnet and release this sort of blocking situation. So this is sort of like the spin mixing with the hyperfine fields and the two exoplexes, or the two Coulombs. So the theory then is very similar, but now we're just looking at a single spin instead of the two spins, so it's just a 2x2 density matrix. We have the coherent motion in the magnetic field, and then we're subtracting out now parallel spin to the magnet. That's what this term is. And then we're adding new spins onto the defect as needed. So this is actually very simple to solve. You can solve for the current. And it looks a lot like the experiment. So here is a perpendicular magnetic field in black. Here's parallel magnetic field in blue. Okay, they're reversed, but this is a voltage, this is a current, so they should be reversed. And the width of these curves is very similar to certain lanthanum and aluminum defects in the insulator LAO. So it makes sense it might be the hyperfine field acting there. And then also, I think most interestingly, is that you can see there's an anisotropy between the two curves. And there's also anisotropy experimentally. And the anisotropy can be easily shown to be 2 in magnitude. And they've plotted several different, using several different currents and voltages, they plotted the anisotropy of these experiments. And they find it to hover around 2. 2 seems to be a relevant number for that data set. So the theory seems to suggest this localized mechanism. What I've been doing recently is a lot of different extensions to this. One is to apply an AC drive to the ferromagnet. We've generalized this stochastic equation accordingly. So this green, which is hard to see, is now rotating. And when it rotates at the same frequency as the Lamarr precession of the defect, you can actually get this sort of resonance behavior. And we believe that you might be able to use this type of technique to measure local fields of defects, or just use it to measure any type of real magnetic fields. Another idea is we could try to treat the nuclei quantum mechanically, say spin 1/2 there, and could we then maybe read in or read out nuclear states through the hyperfine interaction measured in the current? Also, do these defect states play a role in spin pumping is another important question. So I think I'm out of time. That's fine because I'm done. So I've showed you my work on spin coherence and spin correlations in a couple different systems. And the applications, I think there's a lot of fundamental physics and about spins in disordered systems and localized systems that can be looked into, but there's also a lot of real-life applications. Solar cells actually also are relevant for this. OLEDs are basically the inverse of solar cells, so you might expect similar phenomena. Another thing we've looked at is optical retrieval of magnetic data, where we use fringe fields from magnetic domains, and we can map those out optically to the organic semiconductor. And then I think the medical sciences and the biological sciences are other areas that could be pursued. So thanks for your attention.
Yes, we have time for very quick questions, 2 or 3 questions, about 5 minutes. Questions?
So, in the organics part, you didn't consider any spin orbit coupling, correct? Or it's very small?
Yeah, we consider it to be very small. We essentially ignored it for these purposes, yeah.
And you did briefly mention that you were going to put some heavy ions or metals in there. So, at some point you said that.
Yeah, I did. I probably should. I was trying to explain. Yeah, I was trying to explain how you get the large phosphorescence out, but we didn't look into that at all.
But that has nothing to do with spin orbit coupling. You're not putting that in there to
No.
enhance spin orbit coupling.
No, we're not really concerned about the spin orbit coupling. I was just trying to mention that
Okay.
you can increase the triplet yield by doing that.
On your electrically conditioned devices, you said that you put a lot of current for a long time through them.
Okay, maybe I said think about that. So I think I showed, I think 15 minutes they showed. Maybe that's not a long time, but
15 minutes of
15 minutes at
DC
2 milliamps DC. So I guess they said it was a long time. But I think they went further, but they maybe saw no effect. I think if they went too far, they would see the effect start to degrade. So there was sort of a sweet spot they hit there.
Do you guys think that that's more related to the, let's say, integrated amount of charge that is passed through the device, or just to the self-heating that results from driving more power through it?
Well, I think, I mean, if you have detect too much heating, you could probably also change the, you can induce traps. So yeah, I don't think we know well enough how those are being degraded, through what processes. But this conditioning is seen, and we're not the first ones to see the effects of conditioning. It's well known for a long time that they put traps in. So.
There's this one plot you had of the temperature dependence. There's two temperature curves, one at 50 Kelvin and one at 300 Kelvin.
Yeah.
So I didn't quite understand that plot. So was it about time scales? Because it seemed to show that temperature was strongly suppressing the intensity. Yeah, there.
All right. Okay, so the 50 Kelvin is the red. Okay, so that's a very long, you can tell this is a very long-lived state, right? And these are the triplets because they're essentially not decaying. We want this to be fast because we want to get fast emission out of these OLEDs. So the red is very slow, and that's a negative. And the black, which is at 300 Kelvin, is much more rapid. So that's the.
So in terms of integrated, I mean, that little bump there, because it's on a log plot, I'm trying to understand why you're getting this, at short times you're getting the same or even less intensity, and then it's dropping off very quick, much faster than the other case.
So the short times is definitely the initial singlets that you're putting in. So 25% or so are going to be those singlets, and they're going to have the very fast decay.
I mean, I'm just trying to correlate this plot with when you show the massive enhancement later on with increasing temperature.
Let's see. Okay, so your delayed fluorescence is coming about from basically sort of this activated spin mixing process. And you're creating a faster luminescence. Oh, for one thing I should say, this is maybe a little bit deceptive how I plotted this. This is a photoluminescence. So in essence, this isn't really the electroluminescence of the OLED. So it's a very different process to get to this case is for the electroluminescence. Here you're initially creating singlets, whereas in the OLED you're creating singlets and triplets. So I think my answer would be I wouldn't read too much into this plot, how it relates to the MEL I showed. The main reason for this plot is just to show that there is this delayed fluorescence.
Okay, I think our time is up. I think I was